Hi there. Today we will learn about a model of a time series which is an ARIMA. Time series is a method on the basis of a past data set we can predict the future. On the left side we have a graph, and on the basis of a that graph we can predict some of the observations which are on the right side. Then we have to apply some autoregressive integrated moving average, which is an ARIMA. ARIMA is mostly based on correlation and moving average. We will learn about a practical implementation, and to implement the operation, we firstly have to require some of the required libraries. Stack models is one of the required libraries for the mathematical operation. And after importing all of the required libraries, then we have to load the data set. We acquired a stream CSV file from the local system to our Jupyter notebook as df underscore ice cream. The dataset has two columns, date and the name of a label. After acquiring the dataset, we have to apply some filtering. Firstly, we rename the column, then we have to change the index because in time series, the index must be a time or a date instead of a number from 0 to infinity. Here is an output where on the left side we have a date and on the right side we have a production. The acquired information is visualized in this graph. We have a total of 10 years data set where it begins with 2010 and up to the 2020. Each year we have a cyclic trend, and the trend shows we have an maximum height of approximately 140 and a minimum of 70 in 2014. So there is 10 years, and all of the years has a cyclic trend with respect to the requirement of the product in the market. However, in the time series, for the better modeling of the time series, a data set must be a constant mean, constant variance, and a constant correlation. Here in the example, you can see the dataset has a mean constant and the same variance and the same covariance. Similarly, when we implement the operation, you can see our model has the same mean. Then in the case of a variance, we have somewhere high variance. But in the cyclic trend, there's a chances we have a high variance because of some outliers, errors, and some random fluctuation. So here we have a two fluctuation in the beginning and in the mid, such as 2016. Then we have to do some plotting, ACF plot and the PACF plot. These plots are required to analyze the lag. In ARIMA, we have a lag PDQ. We will learn about PDQ in the future. So here we have ACF plot which defines how many observations are required or are useful for our model. In autocorrelation, it's a correlation between all of the observations, and here you can see there are 1, 2, and 3. 3 are the best observation in the whole of the data set. So here static lag 1, or you can say static lag 6 and static lag 12 are on the highest static lag, and the remaining are behind them. So we will use static lag 1, 6, and 12 for our model. And with respect to the autocorrelation graph, we use a moving average. So to know about the value of a moving average, we can use autocorrelation. Similarly, to find the value of autocorrelation, like autoregression, sorry, then we have to use PACF plot. In PACF plot, we have 1, 2, 3, 4, 5, 5 observation. On the basis of that observation, we can apply some method for regression. So here in the PSC approach, you can see there are some of the points which are above the statistic significance. The graph or the opaque side, which is on the from the plus 25 to minus 25, it can't be used because it's not a statistic significance for our modeling. The points which are useful are the highest lag. So here you can see the first one, second, then third, fourth, fifth, sixth, and this one seventh, then 10th, then and 13th. So here we can say for the auto-regression, we will use 1, 2, 7, 10, and 13 for our model building. So after acquiring a parameter for AR and MA, we are ready for the modeling. Then we have to split the dataset into training and testing. After splitting the dataset, we are ready for the model building. And after model building, the model are acquired the information, and with respect to the AIC, we can evaluate the model. However, in AIC, the least value we have, the complex model it will be. So here you can see we have a minimum 679, then we have a 677, then we have a 647, and I think this one is the least value. Yeah, this is a 649. So ARIMA 1016, where 10 is auto-regression, 1 is a differentiating, and 6 is a moving average, is the best model. So after acquiring the best parameter for the ARIMA, we will evaluate the model again with respect to our requirements. So when we implement the operation, here you can see we implement best model AIC, and the parameter we have 1016, which are developed by the above model ARIMA. Here the coefficient is a minus for the auto-regression 1, which is a minus 0.37, and it has a p-value 0.260. And then we have ARIMA 2, sorry, auto-regression 2, it has a coefficient 0.026. So these are the parameter or parametric evaluation of the model with respect to the 1016 as a hyperparameter. Then after building the model, we can predict the observation, and here the visualization set, the blue line is a data, and the yellow line is a predicted observation. And then we have to find some residual. Residuals are the error in which we have some actual minus predicted observation. It's like a differentiation between the actual, the existed observation minus the predicted observation by the model. And after having the residuals, we can evaluate our model performance. Here you can see our model perform very well. It's 3.43% error. It means only 3% of the total observations are incorrect. However, we have 96% observations are true. So our model perform good. And so in the end, we can say our model perform well. With respect to the requirement, it gives an output with an error rate 343. So we are pleased that we developed an ARIMA model for our time series. Thank you so much.